Okay. I'm sorry we couldn't get you some coffee, but I'll hope to entertain you for the next uh, lecture, which is going to be about setting up targeted proteomic experiments. So how many of you finished tutorial 2? Great. Maybe someone can tell me, did everybody understand what is the meaning of each one of these columns? Somebody would like to tell me what was at the end of the tutorial we said open the exported CSV and make sure you understand each one of these columns. So what were the columns? If you didn't do it till then, don't do it now. I'm just asking if anybody already figured it out. Okay, so the first, go ahead.
One is the precursor ion.
Mm-hmm.
And one is the sequence of the peptide, the collision energy, and 0 is, I think, this declustering.
Exactly. And so, there's another column which you didn't explain?
The fragment ion.
And another one which you didn't say anything about? What's this? There's a number there that's equal to all of them.
The number?
Would be
20. The cycle time. Oh, dwell time?
Dwell time.
Okay.
So we have Q1, Q3, dwell time. Then we have some sort of ID, some identification of this transition. Then we have, in this case, the clustering potential. This has to do with how we set our settings. We said use none, so we get everything with a 0. And then we have collision energy. And the purpose of this talk is actually to go through each one of them and actually explain to you how do we get to this. So now you've just did a tutorial where somebody already generated the library, we updated the library, and we generated a transition list. And now we'll go through all of these columns in a lecture format to try and understand what are the different considerations when we want to get to this transition list. So how did we, in this case, design this list of interest? So again, this relates to this table that you already saw and will see quite a few times. First talk that we heard from Tina, we addressed how do we choose proteins, peptides, and fragments, which would lead us to these precursors and fragments. At the end, what we saw in this table that we exported is this list of Q1, Q3. So Q1 is the precursor, Q3 is the fragment. And then there were different other parameters that we need to give to the mass spectrometer. In this case, I also mentioned retention time, which is something optional that we can enable in measuring. And there are some prior knowledge that we're going to talk about how to discuss. So there are 3, and we've said in the last talk that the nice thing is that it takes a lot of, the bad thing, it takes maybe a lot of time to get to the table unless you can download it from somewhere or somebody already made it for you. But once it's developed and you can always use it again, then measurements can take some speed. And what we'll do in the first part of the talk is talk a little bit more about selection of the transitions. So to continue a bit on what Tina started, then we'll talk about these columns, what is it, dwell time, how do we work with retention time, how do we work with collision energy, and the third part of this talk will be about these normalized retention times. So Tina already mentioned it this morning, and we'll explain a bit how does this concept work and how is it implemented in Skyline and so on and so on. So the idea is that the aim of this lecture is that at the end of it, you understand each one of these columns and able to look at a transition list and understand what's going on and what were some of the decisions made in order to generate this transition list. Just a question before I start. How many people are working or interested in working in with triple quadruples or SRM? Okay. And how many people are interested in doing PRM? Okay. Most of the slides I'm going to be presenting are related to SRM, and we'll get to PRM during the week. Some of the principles apply equally to PRM, and then I'll try to highlight this applies equally. But please note that some of the things are specific to SRM, and I'll try to mention this. So from in the previous talk, what we said was we're going to be using a library for selecting transitions. We talked, Tina mentioned to you, the best place to start with is empirical data, and then we said we would like to do 2 things. One is to select the most intense transitions per peptide for maximal sensitivity, and the second thing we would like to do is to choose the unique transition signature for selectivity, so to make sure that we're targeting the peptides that we're interested in. So why not measure all the transitions? That's actually a viable thing that you can do and was done in the past quite often, you could take a lot of instrument time and just measure all possible transitions for your peptides of interest, and then just select from the chromatograms a set of the most intense transitions. So in this case, it would be the most intense peaks. And then we can also look at the list of transitions when we've measured all of them, and then manually select those that will achieve the maximum selectivity. So this can be done, and I'll mention another way of how you can store it afterwards, but it usually requires a lot of instrument time and is mostly performed when you have synthetic peptides or synthetic proteins, but it is a viable option that you should bear in mind as an option. So you don't always need to have a library, but the most common thing that we do is we do a library, and even when we work with synthetic standards, then sometimes we generate first a library out of them. And there have been several workflows in literature. One where you started with synthetic standards and then you generated on a Q-traps or on the same machine where you would do the measurements afterwards. You would generate using these synthetic peptides assays for peptides that you're interested in measuring. Another approach that came in 2011 was to take proteins that you're interested in, express them in a certain system, digest these proteins, and then generate assays for these. Of course, the advantage when you work with a digested protein is that you get one extra level of information, and that is that you also know which of the peptides flies the best. So you can tell these peptides are the most likely to be able to be observable from all the peptides of a certain protein sequence. So when we just order a synthetic peptide, we don't know how well does it fly compared to all other possible peptides. When we digest the protein, we have that extra layer of information. But whether we started from a synthetic version, whether we started from a digest of a complex sample, wherever we start, then most often we would do selection of optimal transitions, and this we will do from spectra. Then we would need to know, as mentioned already in the questions, what is the dominant charge state, whether it's +2 or +3. These are the most common charge states that we use with targeted proteomics, but they are not necessarily the only ones, so sometimes we need to look beyond these two. And then we would like to know what are the relative intensities of the transition, of the fragment ions, such that we select the transitions that we're interested in. And these charge states and fragment ions are basically prior knowledge, so we need to obtain this from somewhere. These can be very machine dependent and vary from machine to machine. I will address this in a couple of slides a little bit further. And the way that we store all of these and use it is in a spectral library. So that is a collection of a lot of spectra that we can store. And how do we get to this? Well, we can start to get to a spectral library. We can start from shotgun data, PRM data. There are even ways of getting from SRM data, so something called SRM Trigram MS2. Nowadays, you can even start from data-independent acquisition and try to search it. And then what usually happens is that these types of data are converted somehow, either by ProtoWizard, by a vendor's converter. They are searched by different search engines. And of course, these days there's a lot of search engines that are available out there. Many of them are also compatible with Skyline. And then what happens is that you need to build a library, and this will be your reference spectrum. And this step of building the library can be done by several software. One of them is Spectrust, one of them is BiblioSpec. BiblioSpec is the one that is implemented in Skyline. So basically, this part of building a library and using reference spectra is the part that you can do in Skyline. Whereas this part, searching, data conversion, etc., is done up until that point. You can look on the Skyline website which of the search engines and conversion and so on are compatible with Skyline such that you can implement them. And what you do in tutorial 3 is basically to try and go through this workflow. So tutorial 3 is based, in tutorial 2 we gave you a library. You saw that the ending was SPTXT. So this library was prepared by someone in advance, and then you just needed to upload the library and then use it. And tutorial 3 is aimed for you to learn how to build your own library. So you take some search results, you take some files, and then you put some filters on them, and what you get at the end is a library file which is inside Skyline, and then you can use it. So that when you go to your home laboratories and you want to build your own libraries, not always they're available or downloadable, then you would need to build from your own data, and you would basically be following something similar to tutorial 3 in order to be able to do it yourself. And the last thing I want to measure, so we will hear much more about library building, especially because this has a lot of implications when we do DIA. So we'll hear a talk where we will talk more about how to build libraries. And the other thing that I would like to mention is that with certain techniques, you can, as I've mentioned, instead of building libraries from spectra, you can also build libraries from chromatograms. So if I've had here a chromatogram of all the ions, I can basically use this as my reference. It was built from a synthetic peptide. I believe that this reflects very correctly my synthetic peptide of interest. And then I can use this as a reference and then build a chromatogram library instead of a spectral library. And that is also implemented in Skyline via using Panorama. It's a topic that we don't talk about in the course, but you should be aware that it is available for you in case you're interested. The second thing that we said was we want to select, first thing was to select for maximal intensity, the second thing was for uniqueness. And to give an example, and we were talking about these lower ions. If we look at these two peptide sequences, which I just made up as coming from two different proteins, these two peptide sequences would have the same Q1. They have the same mass. All I did was to shuffle here the sequence. And if I choose Y3, 4, 5, and 6, so that's 4 transitions, but these are small Y ions, they are actually shared between the two. And that means that when I see this peak, and I have coeluting transitions and so on, I'm not sure if this peak relates to this peptide, hence to this protein, or this peak relates to this peptide and hence reflects the amount of this protein. So when we think about selectivity, then we need also to think what are the options. And so selectivity relates to what is the background proteome. If, for example, we only had this protein in the background proteome and this actually doesn't exist, then of course that's not a problem. But so we need to know what is the background, and this is not something that we can tell you. It relates to you. We need to think how many transitions we're going to choose per precursor. The more, the merrier, and that will increase the likelihood of selectivity. And then whenever we look at the smaller smaller types of ions, so the Y3, for example, or the B3, then it is likely to be, or it can be less selective. That doesn't mean that it's not very good for quantification. It can be very useful and very abundant ion for quantification, but for selectivity, so being informed that this is the right peptide, it might not be useful. And then selectivity can also be experiment dependent, so maybe a certain protein is expressed in one sample and not expressed in another sample, so we don't encounter this issue in one sample, but we do encounter it in another sample. And within Skyline, there is one tool called SRM Collider. There are other approaches out there that are implemented, but within Skyline only one, where you can actually test, you can put some inputs into this tool and get some information about the selectivity of the transitions. These tools, of course, work only at the theoretical level, so only by trying to analyze a certain background proteome and saying what is the likelihood that I will encounter other combinations of these masses elsewhere. Now, the second instance when we said we would like to select the correct peak was when we looked at this graph, and then we zoomed in on these two peaks, and we said let's compare to a library spectrum, and then we get this dot P, and this dot P, which is higher here, it's closer to 1, will point us to this will point us to this peak as the likely peak. Does anybody or would anyone like to explain very simply what is a dot P, or how is it calculated? In this case, we're doing SRM. You can try. If not, there's a slide.
Sorry, do you just multiply the values of the intensities or something on a scale of 0 to 1?
So he suggested that it's multiplication of the values of the intensities on a scale of 0 to 1. No, but something. So let's say we have a certain peak, and we would like to, and these are the transitions that we measured for this peak. And then the question that we basically now ask is in SRM, and this was a little bit touched on by Rudy, and we'll go more into this, is this peak really the peak that I wanted to measure? So we've seen just now an example where I saw a nice peak, a theoretical peak. I measured 4 transitions, but I'm actually not sure if this is the peptide that I wanted to measure or not. So it's a statistical question. What is the likelihood that this peak represents what the peptide that I think it should represent? And on the other side, what we have is a spectrum that's stored in a library spectrum, and that is matched for this sequence. And this went through the statistics of the search, and now what I would like to change the question is, how similar is this peak to this spectrum? So very simplistically, I'm putting it here that we changed the question to a similarity question. And in order to do this, we need to change a bit the axes. So what we do is we take the relative intensities of the heights or the areas of these different transitions, and then we get something from these relative intensities. We can spread them over an MZ, and then we can ask how similar are these two. So we see that maybe this is here number 1, number 2, number 3, and number 4, and here maybe this is 1, 2, 3, 4. We can calculate there are different ways of calculation the similarity between these two. This is of course a simplistic explanation of this, but one of the ways in which we do this calculation is to do a dot product, which looks at the so the way it's done in Skyline is by contrast angle, and this gives you a score which is between 0 and 1. Now 1 is very, very good, but we cannot say what is good and what is not good in a certain experiment, because this relates to our expectation. So the higher is always better, but lower relates to how much did we actually expect this to be similar to this. So it can be that we never thought this would be similar to this, and then we don't get a very nice score, and then we cannot really say, is this good or is this bad? Of course, we can always use the same principle of a dot product between 2 chromatograms. So we can compare 2 peaks and ask how similar are these 2 peaks in the same way. And this brings me now to the point of the fragmentation pattern. So ideally, we would like to generate the targeted assays on the same machines and in the same conditions, in the same sample backgrounds, as we would also do the targeted, as we would also be doing the acquisition of the targeted data. And this is because when we move between fragmentation types, when we move between machines, we can get different types of fragments. Their relative abundance can change, and then the compatibility, so the similarity between where we got the spectrum from and where we got the targeted data from, so in this case it was SRM data, they might not be very similar. And then we would get a dot product which is not very nice, and we cannot know, is this a bad dot product or a good dot product? And there are different ways of comparing machines, so it depends a lot on how the precursor selection is done, how the ions are being transferred even before the Q1, what type of fragmentation, how are the fragments analyzed. And this is a table that was downloaded. There's a fuller table that was once published by AB Psych, so that kind of tries to rate what is the kind of very simplistically what is the match between the two. And of course, it's not very ideal to use ETD for fragmentation and then try to do SRM where you would be doing CID. And usually HCD is closer to CID than, for example, on an orbitrapic cell, where we have a different type of fragmentation. So these different types of fragmentation can now result in different types of spectra. This results, which results in different types of similarity score, and then we have to kind of judge how is it similar, is it not similar, we don't really know. So whenever we're using an empirical data source which comes from somewhere else, or the first thing that you should ask yourself is, or at least be aware that there are differences between instrumentations. This data could have been acquired by a very good instrument, but just very different from the instrument that you're using, and then what you expect as a dot product should change accordingly. And these variations between fragmentations also don't apply to all ions in the same way, so maybe Neutral losses would behave differently between different instrumentations. We know that Y ions are usually more conserved than B ions, so maybe this is one of the reasons why many people in our lab, for example, prefer to use the Y ions. They're useful for many reasons. And then recently there was also a tool that was published that allows you to judge the conservation between peptide fragmentations between different platforms or within the platform between different fragmentation types. That was published in 2014. So if you really want to make a systematic comparison between different types and you have enough spectra, then you can also get a feeling of it. If not, you can also try, there are ways of maybe doing it within Skyline, but please be aware of this issue. And just to give you a practical example, this is from the from the material that you have in the course. We have a certain peak that we measured. We measured here 4 transitions, and all I did, you'll have now, soon enough, you'll have 2 libraries, and all I did was to go to this peptide, activate 2 different libraries. So this is one library and this is another library. These libraries were generated a bit differently, so the fragmentation was a bit different. And what I hope you can see even from the back is that here the dot product is 0.7, and here the dot product is 0.96. Now I can reassure you that this is a heavy peptide, and I'm sure that this is the right one, but I generated 2 different libraries in different conditions, and so the similarity between this and this can vary considerably according to the conditions in which I generated this library. What this results in is that if we have a spectrum and we are no longer sure how similar it is, this has 2 implications. One, we're not really sure that we picked the most intense transitions. So we wanted to have the best transitions, but if we are not sure that this will behave similarly to this, then we are not sure that these are really going to be the most intense when we move on to SRM. And the second is what I've just pointed out, that this uncertainty in identification, we get a lower dot product score, and we don't know where it comes from. Does anybody have an idea where what could help us with a situation like this? We mentioned it in the first talk by Tina. What was the 6th criterion? Retention time could, yes, but sometimes I don't have retention time, so without synthetic peptide. So whenever we have a heavy synthetic peptide that we have ordered, we normally trust the company that they actually produced what we ordered, and then we expect that they will have the same chemical properties. So the first thing that they should do is they coelute. What you see here is a certain peak. The light is in red, the heavy is in blue, and they should coelute perfectly. And what should also happen is that because the heavy and because they are chemically identical, they should have all the same types of behavior when it comes to fragmentation, ionization, and so on and so on. And so now we can change a bit the question and ask, if I measure these transitions for light, how similar is this to a heavy, so to a synthetic reference peptide or a synthetic reference protein for that matter? I can ask how these 2 chromatograms are similar, and again I can calculate a similarity score, and here it would be called R.P, and this you will see afterwards in Skyline, and we would expect that these transitions coelute, and we would expect a very high .P, because in this case they are ionizing and fragmenting basically at the same time. They should have very, very high degree of similarity, and if they don't, that should ring some bells, and we should go and check why is that. So when we have a synthetic peptide, then we can always use this R.P. If we have a library and we look for a match, we should be aware that we want to have the library generated in conditions as close as possible to those in which we're going to do our measurements. Up until this point on selection of transitions, does anybody have any questions? No. Good. Then in order to create this transition list, the next thing that we need to do are the mass spectrometric parameters. And again, here I'm going to be talking about SRM mostly, and there are different things that we need to think about. collision energy in the Q2, how much dwell time and cycle time. So this was one of the columns that we just filled. So how much should I put there? What should I do with my chromatography in this respect, and so on and so on. And I have to say that these questions here don't apply only to SRM. So I'm going to present it through the lens of SRM, but when we do SRM, then we select certain transitions. If we're going to be doing PRM, then in that case we'll be selecting precursors. If we're going to be doing DIA, then we will select certain mass ranges and how to set up a certain window. Even if you haven't heard of it, we'll explain a lot about how these things work. But all of these types of acquisitions will all face some issues related to collision energy, issues related to chromatography, how to decide on a cycle time to make the best use of retention times. So the first thing we're going to be talking about is collision energy, and this will be in respect to SRM, but we'll try to also highlight that some of these criteria will apply in one way or another to other techniques. And here in SRM, the collision energy, as you can see, is per line. So for each one of these pairs, a precursor and a fragment, we set a certain value, and you've seen this in the table that you just exported. And actually, it's just one of many potentials that you can apply in the triple quadruple. All along the path of the ion, there are certain voltages that you can set. Collision energy is the only obligatory one that you have to set, but there are certain other options which are optional. For example, the declustering potential, you can set it on per fragment, or you can set it for all the fragments. Different values on different lenses again can be set by the user or set once for the machine. The aim of all of these different voltages is basically to get as many ions to the detector as possible, which is basically our sensitivity. So when we think about setting different voltages, what we try to improve as much as possible is the sensitivity. So to get more ions means to see more of our peaks of interest. The collision energy, which is the only obligatory one, is the offset that is applied to Q2. The higher collision energy we put, that gives more kinetic energy to the precursor ions, and then when it collides with the gas, then we would get fragmentation, and hopefully we're hoping that this will derive more ions towards the detector. For each one of these ions, we set a different collision energy, but what we usually see in what you've seen now in Skyline, and what you also got from the vendor when you looked at your machine, is that you get this kind of formula where for each charge state, so for +2, +3, we get some sort of linear formula with certain parameters. Some of them are already implemented in Skyline. You can also add yours, and then these are how the collision energy are calculated per precursor. So we would set here for certain vendors, there's already some formula. You can add here 4, you can change these values, you can set your own, and this will then be used every time that you export a transition list. You can also try and optimize this. This has been more popular in the past, where the idea was to try and maximize the peak intensity in order to gain basically more sensitivity, and this is done by trying different collision energies and seeing which one gives us the best sensitivity. And there is a tutorial on this which we are not going to do, but you have on your drives, in which you use Skyline in order to do this procedure. You can generate a transition list for optimization, you do the measurements, and then what you get at the end when you upload the data, when you get these peak areas, this is the sum, in this case the sum of all transitions. Each color represents a different collision energy, and on the right when you get the peak areas, then this is the collision energy that is set by the formula, and these are different steps of collision energies that we've tried. And what we've seen for this peptide is that the total peak area at the collision energy set by the formula is almost as good as you can get. So if we would offset the collision energy considerably lower, we actually lose in sensitivity. But of course there are cases where that is not, where the inverse happens. This is the collision energy we've set for a certain peptide by the formula, but we could actually optimize it almost 2.5-fold and gain a lot more sensitivity if we were interested in detecting this peptide. So the problem with this thing is that it's time and sample consuming, and a former colleague in our group, Paolo Picotti, actually did this for many peptides, and what she found that for the majority of peptides it's actually not beneficial. You don't gain a lot of sensitivity, but in certain projects where sensitivity is of utmost importance, then this could be something that you would consider. In case you do these types of experiments, please be aware that somebody already asked me, you can actually store them in Skyline in an optimization library, so such that this information is not just in an Excel sheet, but actually stored also in a document, so that when you export next time, these values will be used. And if you have a lot of transitions, sometimes in our lab we do it with synthetic peptides. We do once a lot of collision energy optimization to actually optimize the formulas themselves. So we improve the formula once per instrument, and then we never do it again per peptide. And that is a possibility, with some restrictions on how to do it carefully. And of course, this can be done for any type of other parameter or voltage that you have on an instrument, but I just give these 2 slides for you to be aware in case you're interested in these types of works. The thing that you need to remember in case you're venturing into that direction is that, as we said, the collision energy is set per each line, so it's per transition. Here I show you 2 transitions from the same peptide, and they were ran with the same collision energies. The optimal collision energy for this transition is this one, probably, and the optimal is maybe this one, which means that for each line along this table, I can actually set a different collision energy. That's not a problem. But there's an implication in this, and that this will severely damage our dot products. So again, there will be very big differences if we now set a different collision energy for each transition, then the similarity between a library and our peaks is going to be different. What you see in this are 2 peaks that were measured with different collision energies. One was +10 and one was -10. And here what we have is a view in Skyline where we compare the intensities. So this is the relative intensities in a library, and these are the relative intensities in these 2 conditions, and you can just by color appreciate that they are very different from the library. And this is also exemplified in this score. So you should always try to remember that what you basically are doing here is you're maximizing sensitivity, but you might be kind of losing certainty in identification, since your dot product scores may change. So again, keep it in mind. Brendan. Isabel has a microphone. A microphone for Brendan.
So wouldn't that be a good case for a chromatogram library? So once you've done the optimization, you could generate a chromatogram library, and then you'd expect your dot products to be quite good.
And of course, if you would also do the same thing with, if you had a heavy synthetic standard, and everything would apply, and again you would have this high R.P, or as Brendan suggested now, you would do at the end of this procedure now a chromatogram library and use the new chromatogram as a reference instead of the original spectrum as a reference. So that's 2 options what you could do to solve this thing. The next point that I would like to talk about is this dwell time. Does anybody have questions till now about collision energy, or? No. So dwell time is basically what we tell to the machine, how long do you want to spend on measuring a certain transition in this case. This relates to sensitivity. The longer the detector is waiting for a certain ion, then the longer we are likely to get ions hitting this detector, which would relate to our sensitivity in being able to detect a certain ion of interest. The second thing that we need to consider is not just how much time we want to spend on each transitions, but also how many transitions do we have. So what's the length of this list? And does who can tell me what is when we take all of these into consideration and the dwell time, what do we get? We saw it in the first lecture, the cycle time. So the if we multiply the number of transitions by the acquisition time, what we get is the cycle time, and that relates to quantitative accuracy. So the cycle time, as we've explained, is the distance between these 2 points. So we have a whole list. We went through this whole list, and it took us, let's say, 3 seconds, then every 3 seconds we would get a measurement of our ion of interest. And so the distance of these between these 2 points, which is a cycle time, tells us how many points we can get on a certain theoretical peak. The smaller the distance, the more likely we are to get more points, which means that we are able to recapitulate correctly this chromatographic peak, which is what we're trying to do when we try to get quantitative accuracy. However, this somehow is a is a balancing act, as we've seen. And this, of course, applies in a different way, though, also for PRM or for DIA. So if we're going to be doing PRM or DIA, the same 3 questions will be asked, but in a different tone. So in PRM, we're going to ask how many precursors we want to measure instead of how many transitions in SRM. And in DIA, it's going to take a different flavor. We're going to ask how many windows we want to measure, but there are certain analogies. And so whenever we ask ourselves about cycle time, we should always remember it applies to every technology, but the flavors of it are a bit different. And as Tina has shown you, one example is when you can try and change the dwell time and cycle time, and with different combinations, you would be able to recapitulate this peak, yes or no, and sometimes maybe you would generate too many points that you actually don't need, so maybe you can actually gain in some sensitivity by playing with this formula. But basically what we want is to have enough points per peak. And so we can do different games. So we can say, I want my cycle time to be 5 seconds, and then I would like to have 50 milliseconds of dwell time per transition. So how many transitions do I have? 100. Then I can say, well, 100 transitions, if I take 5 transitions per peptide, gives me 20 peptides, but actually I also would like to measure both the light and heavy, so I need 200 transitions. So if I'm going to take 200 transitions and 50 milliseconds per each one of these transitions, I will get a cycle time of 10 seconds, and then I can say, well, this is actually not a very good cycle time in my case. It's too long, I will not get very nice peaks. Let's try and reduce it. Let's take 2 seconds and 200 transitions. So what's the dwell time? 10. So basically it's a formula and we just play, but this is something that we would be doing before we go to the machine. So in Skyline you had to click on 20 milliseconds and then it exports 20 milliseconds. It's up to you to decide how much dwell time you want to be spending, but the cycle time is a bit related to something else, and we'll get about it in a minute. But here's just an example to show you how it looks like, not just from one peak. So I've here measured a certain set of transitions. This is the dwell time that was given, and then it's the same number of transitions. So basically the cycle time increased. It was 100 transitions that I measured. By increasing the dwell time and keeping the same number of transitions, I've increased the cycle time, and what you see is that the peaks become very triangular. They're not very nice peaks. You still get a peak, but it's not a very nice peak, and the quantification in this case will not be very accurate. So we would like to avoid these types of peaks by keeping the cycle time as low as possible, but we also would like to take into consideration these other parameters. Question?
So why don't you normalize according to intensity? The dwell time?
So I can repeat. The question was, why don't you normalize according to intensity? You do actually. So each machine, the data that comes out is normalized to intensity, but what is not is the number of points where you get an intensity. So if you only have 3 points, then at these 3 points, the data is actually normalized. The intensity that arrived at the detector is normalized to the dwell time. But if you only have 3 points, nothing will provide you with more points except actually measuring them. Is that clear?
I'm not sure what I mean is, let's say I want to measure for each 2 seconds, and when I know that some of the peaks are very intense, so I don't want to accumulate them for too long, I just give them very short, maybe 2 milliseconds, and some are weak, then I give them, let's say, 50 milliseconds.
Okay, I understood. So what you're saying is, for some give a long dwell time and for some give a short dwell time according to my expected. In theory, you can do this. And the machine will accept different, so it doesn't have to be 20 for all the lines. It can be here 10, here 50, here 100. In this case, what you would still get is that the cycle time would still be the sum of all of them. So you would still need to somehow play, but you don't have to do it necessarily by this simple multiplication. Is that clear? Okay. And so we said we want to keep the cycle time as short as possible. For quantitative accuracy, these usually we want to keep as many possible transitions for selectivity, or because we have a lot of peptides or proteins that we're interested in. And then this we would like to keep as long as possible for sensitivity, and the idea is somehow to balance between them. And you've already seen these types of criteria from Tina, so I'm not going to read them again. But this comes in the context of chromatography, so we cannot do these types of decisions without knowing something about our chromatography. And when I'm talking about chromatography, there are of course a lot of aspects to it. What is the average peak width? What is the height that we would like to have? What is the peak resolution? So how good are we in separating two peaks? And these different types of criteria, and there's many more that relate to our peaks that we're going to observe, are influenced by two groups of things related to our liquid chromatography, what mobile phases we're using, what's the length of the gradient, what's the slope, the flow rate, etc., etc. Things related to our column, how long it is, what's the inner diameter, what type of particles did we use, what's the pore size of these particles, and so on. So this is not a lecture about chromatography. So but I would like to give you two examples of how chromatography relates to this balancing act between cycle time, dwell time, and number of transitions. So let's take a theoretical example where we have a long and shallow gradient. What we would get here is very good separation between two peaks. But if we now make this gradient very steep, we would be squeezing our peaks. We get higher intensity. This is a very schematic representation, so our resolution would be lower, so the ability to separate between them is maybe not as good as before. But now our peaks, the average width is going to also be smaller. And we said that when we talk about our cycle time, we need to think about it in relation to our average width. And of course, that can vary considerably depending on the peptides, but we do need to know something about it with respect to our chromatography. So if we have very long gradients, maybe we would have better peak resolution, although we would pay a price maybe in peak intensity, but then we need to consider lowering our cycle time in order to have enough points across a certain peak. And then if we take different particle sizes or different columns, here's an example where we would take a 12 centimeter of 3 micrometers or 25 centimeter of 1.9. Of course, these different columns would have different pressures and so on. So a lot of things come into this, but our average width, and this is data from Eduard Sabido, with whom we teach a course in Barcelona. Our average width here is 21 seconds, and so he set the cycle time for 2.5 seconds. And with these beads, which give you much narrower peak, he needed to set the cycle time for 1 second to get the same number of points per peak. So the message from these two very simplistic examples is that you need to know something about your chromatography. And for each chromatographic setup, you would have different, and for the peptides you're interested in, you would have different average widths of peaks. And according to this, you can say something about what's the recommended cycle time. And usually in our lab, or I'm sure that in many labs as well, this is kind of known in the lab or needs to be established once, and then you work with this parameter and something around this parameter, so you don't need to discover it each time to begin with. But basically we start with the chromatography, we know something from it about the cycle time, this gives us a range, and then there are two ways that we could go at. We could say, given that this is the cycle time that we can have, what's the number of transitions that I want to measure? This is the list of my peptides that I'm interested in. And then from this calculate what is the acquisition time that I'm going to have per transition on average, or distributed a bit differently according to something that I know about the intensity of these peaks. The other option is to say I want to go for maximal sensitivity. I'm going to, from the cycle time, calculate, try and say what is the acquisition time that I want, how high does it need to be, and then do the calculation and see, okay, this is the amount of transitions that I can squeeze into a certain method, and then maybe I need to do several injections, for example. Now, how can we improve on this? We heard the yes?
Schedule?
Scheduling. Okay, very good. So scheduling, as we've mentioned in the first lecture, is, and this is again a schematic representation. At the beginning we were measuring, let's say each color matches a certain peptide. Let's say 1 transitions that we measured. Of course we should have more, but in this case we've been measuring transitions for these 4 peptides along the whole chromatogram. But if we have some information that this peptide comes around this time and this peptide comes around this time, there is actually no point of measuring transitions for this peptide over here in time, or measuring transitions for this peptide over here in time. So we could actually tell the machines, we have some information about when do we expect this peptide, and according to this we want to start to trigger the measurement of these transitions for these peptides. So we could divide this into several segments and then measure certain transitions at certain times. And what you see here immediately is, instead of measuring 4 transitions, now we're measuring only 1, so we immediately gain in sensitivity. So by having fewer transitions per window, we can increase the acquisition time while maintaining the cycle time, and of course the more of these segments we have, the better. So this calculation works in our favor. And de facto what we do is we don't divide the chromatogram into segments, but we define windows. So we basically say when should we start and when should we finish around this expected retention time of this window. We define a certain window in which we're measuring a certain transition. And the wider the window, then of course this kicks into our acquisition time, so our sensitivity. In this case, now I've defined a wider window, so sometimes I'm measuring 1 transition, sometimes I'm measuring 2, and so on and so on. Sorry. And if I'm measuring here more concurrent transitions, then that means that at certain times maybe I'm losing in sensitivity. So what we do in scheduled SRM, and the same applies for PRM, is we try to increase the number of measurable transitions per run, and this we do by telling, and this what it enables us is to maintain a certain cycle time, which we've defined on the machine. We say, we know from our chromatography the cycle time is 3 seconds, and then we want to gain in sensitivity, so we want to have as many maximum transitions. We increase the number of transitions in each window. We schedule them, so we gain in acquisition time, but we don't compromise the cycle time. And the smaller the window of scheduling, that means that in a single run we can squeeze more transitions into our method without losing in any of the other parameters in sensitivity or in quantitative accuracy, or we can also just keep the same number of transitions, but when we're just gaining in sensitivity. So if we just took the same 100 transitions and scheduled them, we would just have more points with the same cycle time and more sensitivity. The thing that we risk when we're doing scheduling, we might miss the peak. That means that if we scheduled a certain peak around in a certain time along the chromatogram and something happened to the chromatogram, or we didn't know the retention time, we might try and schedule these transitions to measure in a certain window, but actually the peak eluded somewhere after this window. And that says to us that the peak, well, we wouldn't know it. The peak was actually there, but we missed it. And of course, the smaller the window, there's also a bigger likelihood that this will happen to us, that we've missed peaks. So we also try now to balance the size of the window. How many minutes do we want to put on each window? And this relates again to the chromatographic setup. So there are different rules, and of course, how much we know about the retention time. So if we had perfect information about the retention time of peptides, then we could do very, very small windows, and of course assuming that we have a very good LC system. And if we have not a lot of certainty in retention time and we have very long gradients, maybe we would like to have bigger windows. So we also need to know something about the retention times, the length of the gradient, and then accordingly we can set our windows. And as you've so far deduced, we need retention times, so we keep coming back to this issue of how do we get these retention times, or how do we use them. But basically now the balancing axe becomes a bit bigger. We need to know something about our chromatography or play around with it. Then we would like to balance the cycle time, the width of the retention time, the acquisition time, and the transitions. So we would like to play around with all of these parameters in order to set that Excel sheet, that transition list that is what we actually are going to be pasting into the machine. And of course, sometimes balancing all of those don't work, and then we increase the number of injections. So we say, well, we would like to measure it in we need to inject this sample 3 times in order to go through a whole list, or maybe just twice, and so on and so on. All of this is, of course, enabled in Skyline, so you can add all of this information, and then when you would export the transition list, and so far you've just exported one, but you can also say that instead of having a standard, you would have a scheduled method. Then for this you need to have retention time information inside your files. And then the other thing that you can do is you can split it into several methods. You can tell the machine, I would like to have multiple methods and a maximum concurrent number of transitions. And what this maximum number of concurrent transitions means is basically back to this calculation. So if I have a cycle time of 3 seconds and I would like to have a dwell time that is always higher than 30 milliseconds, then I would write here a maximal concurrent transitions of 100. And then I know that it's always 30 milliseconds or more. And this information is implemented also in Skyline, so it's presented to you when you've uploaded a certain list of transitions and you've uploaded some data, so you need to have some information about the chromatography. So the chromatography here would be the x-axis, what's the scheduled time. Then we can actually calculate what is the number of concurrent transitions. So how many, in a certain window, how many transitions are going to fall. And this is presented in these type of curves. Here each color relates to a different type of window. So when I have a 10-minute window, that's when I will have a lot of concurrent transitions at the same time, which means I will have a low acquisition time. And the smaller I make the window, the smaller will be the highest number of concurrent transitions. So in this example, if I would like to have a certain amount of concurrent transitions, I can calculate here, take this number here. So this is just for visualizations, this graph. And then from here I would say, let's take 200, I would put here 200, and then Skyline will calculate here in this number, is it going to fit into one method, or do we need 2 methods, and so on. And we're going to see in the next tutorial how to get to these plots and so on and so on, but it's important that you understand what it actually means. Is there a question about this plot? Is it still clear? Yes? Just a second.
So is accumulation time and or injection time the same thing as acquisition time?
So partially yes. So the injection time is on a different type of instruments that relates to the Orbitrap. It relates to the same thing as acquisition time, but as you know, it also, when you set your injection time, you also need to think of your AGC, of your automatic gain control. So, and these two things already interplay, but relatively I would say, yes, this is kind of looking at the same thing. But with the premise of the different instruments and how they actually function. So, okay. Yes?
The number of concurrent transitions, isn't it dependent on the complexity of your sample?
No, it depends on the complexity of the list of transitions. So it depends only on what you've set in your document. And then let's say you have 1,000 transitions in your document. What this plot does is it looks at these 1,000 transitions, what are the retention times of these transitions, and then it calculates in a 2-minute window how many of them would be concurrently measured. And in a 5-minute window, how many of them would be concurrently measured. And of course, since different peptides elute at different retention times, this is calculated along a chromatogram. So if now I take this information and I go to a gradient which is 2 times bigger, this plot will look different, but it needs information in order to do these calculations. but it's a very useful, handy thing when you just want to get to a certain minimum level of sensitivity, or you would like to make a more informed choice about how many injections you need to do. Then you can use these plots to set these values, and then you know how many injections you need to do and what's going to be your some information about your sensitivity. Okay. So, of course, retention time so far is not, we've talked about it for the purposes of scheduling, but that's not the only case where we use retention time. The other case when we use retention time is for identification. So somebody already suggested that we could use information about the retention time to know if this is the right peak or not. And indeed, whether we're doing SRM, PRM, or DAA, many times we're going to be using retention time actually for this purpose. So we have two very nice peaks, and then we would like to know which is the right one. We can use information that we've stored in the past, where we know that usually it elutes around this time. And when we've done this, when we've projected this information, then we have a likelihood of saying, well, we think that this is the peak based on what we previously known about when it usually elutes. So we're going to be looking a bit on how to do this, but know that there are two uses, at least two uses of retention time that we are discussing here. One is just for scheduling, and the other is for identification, and we'll hear more about this also when we're going to be talking about building libraries. So if needed to remind to everyone, retention time is the characteristic time that it takes for a particular analyte to pass through the system, and it would be TR minus T0, and then it depends on a lot of things. The peptide properties of the sample itself, so what's the complexity, what's the loading amount, properties of the whole system, so what's the chromatography that we're using, the auto-sampler, etc. And of course it's also bound for some unpredictable variations. Maybe there was something clogging, or maybe there's a certain shift as the column gets older and older, etc., etc. And the thing is that retention time in itself is not very transferable. So as we've heard before, if I tell you this peptide elutes at 15 minutes, it's going to be very hard for you to go back to your system and ask what's going on in 15 minutes, because we would need to know a lot of information about these parameters in order to do this. And what we would actually like to do is to change this information into something that is independent. And one option is to go through this, but first we need to get this retention time. So where would we get this retention time from? One option would be to go with unscheduled SRM. So we just measure, for example, if we have synthetic peptides, we could measure them across the whole chromatogram, look for a peak of interest, and then we have information about the retention time. Another option is to take discovery proteomics, so all sorts of shotgun experiments, and then to derive the retention time from it. And actually, when we build libraries in Skyline, you will see that also something about the retention time is also being recorded. And then sometimes when we load targeted assay libraries, then the retention time is already incorporated. Usually it is incorporated in a different value, which I'm going to explain now, but there is already some information about retention time which is available out there. And when we don't have any information about retention time, then we can use prediction for it. So there are tools such as SSRCalc, which this tool, so sequence-specific retention calculator, it's a web-based tool, but it's also implemented in Skyline, and you're going to be doing this in the next tutorial. And there are other groups that develop their own tools. So even if we don't have any information from these types of sources, and there are of course others, so I've just listed a few, we can still get some approximation of what is the retention time. And from this you can also deduce that if these predictions are working decently, then we can always do scheduled SRM or scheduled PRM, because we can always start at least with a predicted retention time and a very large window around this predicted retention time, and this would already give us something in terms of sensitivity, even if we don't have information. But of course, the best place to start is with empirical retention time. But even when we've obtained all of these, then all of these would also be dependent again on these chromatography and so on and so on. So we're still left with these units, these information which is in minutes. And ideally what we're looking for is a way to standardize retention time information so that we can store it and transfer it between us. And this is done by a retention time index, or some people would call it the IRT value, which I'm going to explain now. So let's say we take a certain analyte that we're interested in this case it would be a peptide. It elutes at 11 minutes. And there's a concept that was already established a long time ago in chemistry, and I think more than 10 years ago in proteomics. To find a way to standardize this is to measure it between standards. So what we can do is measure, for example, here two hypothetical standards, standard A and standard B. We know that this eluted at 5 minutes and this eluted at 15 minutes. And what is now very well established is that the distance between these standards is going to be conserved across different chromatography setups. So although this is in 5, 11, and 15, so these are in minutes, there is a way to say what is the distance between these two standards, and that is done by an index. And instead of having this in minutes, now we have it in certain values which don't have a unit, but tell us, let's say that this is the first one, which we could call it 0, we could call it any other number, it doesn't matter actually. If the second one would be 100, then we can say that this comes at 60%, for example, of these two things. And I just use here a percentage as an example. It's not actually a percentage, so it really doesn't have any unit. But I can say that the distance between this is, let's say, 60, and the distance between this is 40. So what is conserved is the distance between these standards, and this distance I can take to any type of chromatography, and it should be stable. We don't usually use the term retention time index, but we use the IRT value, and this IRT value will never have a unit, and very importantly, it can be negative or very high or very low. So it doesn't have a meaning itself, but there is a meaning to the order and the distance between all the values of different standards. So how do we get this IRT value? Let's say we've had an analyte. Now I've told you we measured it, it's in 11 times, and we would like to get to this index. Because this index, as I've told you, is what we can store and transfer. What we do is we measure these standards, A and B. And for A and B, we actually already know in advance, and that's very important, we know what is their index. And then the only thing we need to do is a linear fit, a linear regression between these two. So we take the time axis here, and we take the index here. These should be on a linear curve, so 0 would match to 5, 15 to 100, and then if we know here 11 on this curve, we can just extrapolate and get 60. And this 60 is what we can now store in our database and always use it. So we've moved from time in minutes to an index, and we've obtained a new IRT value for a peptide that we were interested in. Now, there's also the other option. Once we've had these values, we can predict retention times. So in order to predict retention times, of course, we need to have some sort of database, some sort of storage where we have all of these values, both of standards and of the analytes. And these, as I've told you at the beginning, of the standards, they are provided in advance. And then we can try and predict what is the retention time of the analyte. In order to do this, we need to measure the standards in a real chromatography. So now we want to move back into the dimension of minutes. So in this new chromatography, this is going to be 10 minutes and this is going to be 110 minutes, completely different from before. But I can use these values, and then using the same, I'm going to need to make a new linear fit. And then again, these should fit. 10 would fit to 10 to 0, 100 to 110. I have a new linear regression, and then I just take the 60 on this axis, and I would get 70, and this would be predicted to elute around 70 minutes with some degree of accuracy. So basically, by using a linear fit between the IRT space and the RT space, so the IRT is this index retention time which doesn't have any units, and the RT space is the one in minutes, we can move between these stored IRT values into our real measurements. That means that every time that we would like to predict retention times for our peptides of interest, we would need first to have something in our database, and then we go to our machine, we measure only the standards, and based on the standards we can establish this linear curve and then predict retention time for all the other analytes that we want to measure. So it is a much simpler way once we have obtained these IRT values. And this is a figure from this paper from 2011 in Proteomics about the IRT concept. And what this paper intends to show is that this linear fit goes on different type of LCs, on different types of lengths of gradients. You will always get this linear fit between the IRT and RT. And so again, this is the one in minutes, and this is the one in IRT values. You will also notice here already that one of them is negative, as I've stressed before, and we can always get this kind of linear regression. And what we benefit immediately is that we benefit the prediction when we do it with these IRT values is usually a much better prediction than to use an algorithm. So for example, what I show you here is a prediction with SSR calc based compared to the empirical RT versus a prediction with IRT compared to the empirical RT. You see that the spread along it is much smaller when we use empirical, and this immediately translates into the window that we need to set with scheduling, which, as we've said before, immediately translate into what's going to be our acquisition time. So if we can make a smaller window, 4 minutes instead of 20, since this is not a very accurate prediction, we're going to take a bigger window. If we're going to take a bigger window, we're going to lose in acquisition time. And if we're going to use empirical data, so IRT-based prediction, we are more likely to be able to predict the correct retention time, which means that we can keep the window smaller, which means that we're going to gain in sensitivity, we can gain in relation to acquisition time. So there are different ways of or different products that you can work with. You usually you need to use a set of peptides that is spiked or present in your samples. One option is to go for a commercial kit. For example, Biognosys, Pierce, Sigma, Aldrich. These are at least the ones that I know. In our lab, we work with Biognosys, but I know of collaborators that work with other kits. There's also the possibility of developing your own set of standard peptides, so it doesn't need necessarily to come from a commercial source. You can also develop your own things. We would recommend then to use between 10 to 20 peptides that would cover a whole retention time range, so you don't want all of them at the beginning or at the end, because you would like to have a prediction that is as accurate as possible. And then it of course should be of high quality and abundance in all samples. And this can be a set of peptides that is endogenous or spiked in, so maybe you've ordered already a set of peptides and you would like to use them. That is of course acceptable. But then you always need to note that you need these retention time standards in every sample in which you would like to obtain an IRT value or predict an IRT value. So if you're not interested in doing one of those, you are just interested in, for example, just measuring a lot of samples after you've done the prediction, maybe you don't necessarily need to have it inside the sample, although we do recommend it because it also serves as a quality control. But in theory, at least whenever you're interested in the task of predicting retention times or obtaining, of course, for obtaining new IRT values, you would have to have these standards. So just to give you two examples of how this would look like, when you would get, for example, a kit from Biognosys, we use this kit. It has 11 non-naturally occurring. It has 11 non-naturally occurring synthetic peptides that cover a broad range. And this kit comes with a set, as I've said before, it comes with a set of IRT values. So this is very important. We know these IRTs, so what is the relationship between the standards? This is provided to us in advance. Also recently, there was a publication where instead of using spike in IRT peptides, they developed an assay that is based on peptides that are usually or quite commonly present in a lot of samples. This is a set of 14 peptides. Usually they come from contaminants or from trypsin or from some human proteins, or they're almost always there. And you can of course go and check, are these peptides in my sample? And if they are, then of course here's provided the IRT values, and you can just start working with these as a set of IRTs. But again, it's given the premise that they are always detectable in your samples and you can always see them. You can always move between different kits because you can translate these, and this is what's actually done, right? I mean, these are all on this same scale of IRT values, or they can be, so that means that we can move between kits. We can use one kit and then move to the other by recalculating and resetting different types of peptides as standards. So basically we've started with a stored assay. So in this case, let's say somebody here in the lab sent to me a table, an assay table, and I would like to make from this assay table, where I've stored the normalized peptide, the normalized retention times, I would like to actually fill this retention time column in order to be able to submit it to the machine. So when I want to do scheduling, I cannot use these values. I need to actually fill it in with units in minutes. So I need to go once through the process of predicting these retention times. And what we do in the lab is, in order to fill this, as I've said, we take our RT standard peptides, we spike them into the sample, and we measure the RT standards. Then we can get a linear regression which fits for today's machine. So this is the retention times on today's machine, and this is the IRT values that don't change, and we get a certain linear fit. These values would change according to the machine, so according to the scales of the Y, the X-axis won't change, but the Y-axis will, and of course accordingly these values would fit. But once we have this formula, we can just take our stored values, look them up on the axis, and get retention times in minutes, predicted retention times in minutes, and these are the values that we're going to be filling in. And now we basically have a table where we are ready. We have all the information that we need in order to submit a transition list with predicted retention times into the machine. How this table actually looks in practice varies a bit between vendors. So if you work, for example, with an AB Sykes machine, what you're going to be doing is setting this retention time and then a certain window around it. You're going to be so this is the center of the window, and then you say a 4-minute window around it, so +2 and -2. And if you work with a thermal machine, for example, then it's going to be start and end. So it's going to say, in this case, if I have a 4-minute window, then it's going to say 26.8 till 30.8, so a 4-minute window centered around this. And I actually don't know how it works for all the other vendors, but please be aware that this table might look a little bit different between vendors, but the principle should be the same. And of course, all of this is set up in Skyline. We're going to be doing a tutorial on how to actually do this. But basically, we can store a set of standard peptides. These are going to be our IRT standards, which we store here separately. And then we can store within Skyline a library of all the measured peptides and their respective IRT values. And then we can once go measure just these standard peptides, and based on what is stored in this table, Skyline will do, based on this table and what we've measured, it will do the linear fit, and then it will provide us a predicted retention time. And this predicted retention time is presented here as a line which says predicted. I don't know if you can read it, but it is also presented in the chromatograms when we're going to be looking at data. We will actually see where is the predicted retention time, which, as we've said, in this case is also going to be useful for identification. So if I've looked at this peak and I want to know, is this the right peak? I see, well, it's very close to the predicted retention time, and this would give me some confidence on how likely this peak is going to be the real peak. And what we're going to do now in the tutorial is we're going to be first trying SSR calc, so a prediction that doesn't need anything except a sequence and some information about a certain chromatography setup. And then we're going to do once manually this type of linear regression. So you're going to go to Excel and try to actually generate this linear fit and see what do you get as IRT values. So once we're going to try and move from this measured time to the IRT index, the IRT value, and then once you'll do it with Skyline such that you've set up an IRT calculator in your Skyline document, and you can always do these predictions. Are there any questions till now about IRT, about using retention times or anything like this? Yes.
I would like to ask, is your machine reporting that your RT peptide is not behaving right anymore, and you should change your retention windows?
So my machine doesn't, but there are possibilities in which this, I think, is implemented, at least in thermo, where you can set certain peptides and it would update the predictions according to the behavior of the standard peptides. So it would look for them. And actually also in Skyline there's a QC workflow implemented where you try to use this information of what happened to the standard peptides, and according to this maybe change the predicted retention times accordingly. My machine doesn't do that, but
So which instrument is that?
so I work with an AB Sykes with a Q-trap.
And the thermal one, which does do the job?
I think it's not the machine itself, but one of the versions of the software, and I don't know to tell you which one. Yes.
If you're downloading the SRM assay, like if you try to just find some online, does it tell you which of the standard peptides were used to generate this index retention time, so that you could just apply the same ones to your
So
machine?
They were specifically here they use this IRT kit from Biognosys, but once we've moved to this dimension where we don't have any units, all of them should fit into the same dimension. So I've shown you now an example of endogenous and the kit from Biognosys. They should fit each other. So the idea is to move into an indexed unit which is proportional, but then afterwards you should be able to always translate one to another. Yes. Yes.
Is it would it be a recommended practice to spike our discovery samples with IRT peptides, like a QC thing, and because it'll also help you build or extract better information, more accurate information for making the SRM assays. So do you do that ever? I mean, spiking the discovery samples with IRT peptides? The DDA experiment, I mean.
So yes, if you would like to generate IRT information, it's better to do it to start adding these as early as possible. So right from the first shotgun experiment that you're going to be using to build the library, that you're going to be using to then generate SRM assays, for example, if you would have along all the steps also the IRT peptides spiked in, or any type of, so not necessarily this kit or another kit, you can also use the endogenous one, but the moment the earlier you start to work with this, you can then add to this table, you can ask Skyline to calculate from the shotgun data these IRT values, these would be added, and then you immediately can start to use these values. So best not wait if you want to start using this information. Any more questions? Yes?
I would like to ask about chromatography. So for shotgun, typically one tries to aim for a best resolution possible, and it seems that's not the case for the targeted SRM experiments.
So I think that varies considerably between labs. Certainly, I can tell you in our lab, we try to make the SRM runs shorter, so our gradients would be 30 minutes or less, and then by this we also gain in the throughput of samples, so we can inject many more samples and use shorter gradients. I certainly know of other groups, and you can see of course in papers that other groups would use longer gradients for PRM or for SRM and so on, so I cannot tell you which one is the best. There are advantages and disadvantages to these decisions. In this context, the main thing I would like to highlight is that what you choose for your chromatography may implicate other decisions. So it will implicate your cycle time, your sensitivity, and so on in these calculations. And of course, if you have a very short gradient and a very complex sample, you can maybe have more ion suppression, so you might actually be losing some of your signal that you're interested in just because of these effects, which have nothing to do with the calculations that we've mentioned here, but things that have to do with the ionization and fragment, just before even fragmenting. In that case, I would just like to very briefly summarize. So in this talk, we went through this table to enable you to make some aware decisions on how to create this table, and basically submit it to the machine. I've talked a little bit about juggling between these different parameters: acquisition time, cycle time, what we know about our chromatography, how many injections we want to do, what's the RT width that we want to know. And this is a bit of an art to try and decide how to balance all of these, but it is a very achievable art. And then basically, as a summary, in the first talk we've been talking about how to find the best flying peptides and the unique ones for selectivity and sensitivity. Then we talked about, we started in the previous talk and in this talk to talk a bit about the intense and unique transitions, and we talked a little bit about the difference between machines and how this can implicate this information. And then that's where basically comes in the issue of relative intensities for selectivity, for making judgment of these dot product scores. And then here we talked about collision energy and how this implicates sensitivity and whether we should try and change it or not. And then we talked about how to determine the cycle time based on our chromatography, and according to this we can say something about our quantitative accuracy, and from this we can go into juggling the other parameters that we would like in order to maximize each one of them. So one thing that we mentioned was that we would always like to maximize the dwell time and the number of transitions, but we need to balance these two for terms of sensitivity and what we actually want to measure in our project. And then at the end we talked extensively about finding the accurate retention time and talked about how this is informative for sensitivity, for scheduling, and for selectivity, for identification. And we'll see a bit more about how to use this information for identification when we talk about building assay libraries. So if anybody has any more questions, I'm open to questions. If yes.
Just one small question. So in your experience, how good is the Y4 ion in actually as a transition for quantitation? I mean, I know it's too small. Is it too small? I mean, it is a small peptide or a small fragment, but how often is it used, like, for quantitation? Or would you just?
It would be very hard for me to answer this question. If Y4 is from a very small peptide, it's a very different Y4 from a peptide that is 35 amino acids long. So in terms of selectivity, this relates to the length and sequence of the peptide. If Y4 is just R, or there, it's very hard to make a statement about one type of ion. It is, we can say that the shorter the ion, the smaller the ion, so a lower M over Z, there's more likelihood just that there are more types of peptides that would lead to such an ion. But that should not exclude it for the purposes of quantification. So we can have an ion that is not very specific, but in this retention time it has no interference, and then it would be a very abundant ion. And I think in certain machines you would see this, for example, for the lower B ions, you would get very high peaks, but then they could be interfered, and they could also not be interfered. So the decision on when to use it or not is with respect to data, not just by guessing. Any more questions on this? No. Good. Do we have coffee machines or not? No? There. So do you want to do the break now or continue with tutorials? I would say the following. We now need to continue with the tutorials 3 and 5. If you feel like you need a break, the coffee machines are actually working. So you can also take a coffee break at any time. You can continue working with tutorial and take a break later. You can stay, you can do whatever you want. We would like you to get through tutorials 3 and 5. So according to how you've progressed so far, please continue. There is, no, it's not in your folder. This thing.